Hi.
Hello, how are you?
Good. How are you?
I'm fine.
What?
I'm
Sorry.
fine.
Nice.
Let's see. Does that sound different?
Uh,
No.
wait. No.
I changed microphones.
Oh, no, it's still good.
All right.
I'm looking for the files that you just uploaded, but I don't seem to find them in Moodle. Maybe I should just click on download.
It should be attached to the email.
To the email. Let me try.
Shall we post it on Moodle?
I
can do that.
it doesn't seem to work for me, but
All right, let me stick it on Moodle.
thank you.
We're just going to put it up in the top section.
Okay. Thanks.
Yep.
Here.
Okay, so I created a thing called data at the top, which has the data sets in it.
Okay. Yeah, I see it. Thank you.
Yep.
Professor, I have a quick question for you.
Okay.
So I was going through the notes, and when you did the PR change command on Stata, it said it was unrecognized in my state. And I tried installing different things that allowed it to work, and none of it seemed to function properly. I was wondering if you had any suggestions.
Well, yeah. So I talked about PR change the other day.
Mm-hmm. The last video you posted.
All right. So PR change is part of a suite of commands called spost. And in the book by Long and Fries, they created this thing called spost. And spost has a lot of different commands in it. And if you want to use the commands that are in the Long and Fries book, you need to install spost. And somewhere in the book, actually, you can just Google spost. It's just S-P-O-S-T.
Okay.
I'm sure at the beginning of the book, yeah, it tells you where to go to get it.
All right, I'll look in the book.
So I had been thinking that rather than having everybody install SPost, I was going to do some stuff with things that are actually built into Stata, because I thought it might be a little bit easier.
Okay.
But you can do it either way. What's happened is Stata has a programming language built into it that's completely open to everybody in the world, and there are lots of people who've written commands, and the good ones, Stata has a tendency to build in to newer releases, and they've built a lot of the SPost stuff into the newest releases, which is what you have.
It's actually really helpful that they're willing to update it like that.
Yeah, it's yeah, that's how they are. They're good. All right. So what I want to do is to start over, and mostly I want to talk about estimation issues today. And so here's what I want to do. Let me, all right. There we go. So, binary dependent variable. Dependent variables that have two values. There are basically two approaches for estimation when y is a 0, 1 variable, when it's a dummy variable. And we have some model y is x beta plus epsilon. There are basically two approaches to estimating the betas in this model. One is to use ordinary least squares, which people like to call a linear probability model. And so if we have x and y, and the y's are either 1s or 0s, what we're going to end up with is a data set maybe where we have a bunch of y's that are 0 and y's that are 1. And if our data set happened to look like that, the x's can be any value, but the y's are only 0 or 1. If we have a data set that looks like that and we estimate it using ordinary least squares, we get a regression line that passes through those points. And the thing we don't really like about that regression line is that it predicts a negative probability, right? So for x star, what this says is, this is y star, which is the probability that y is equal to 1. And so essentially we interpret these fitted values as probabilities. And the thing we don't like about this model is that for large values of x in this case, we can get probabilities above 1. For small values, we can get probabilities below 0. And that's uncomfortable. And so to avoid that problem, what we'll do is to use maximum likelihood estimation. And there are two models that are commonly used. One is called Probit, and the other is called Logit. Probit is based on a normal distribution, and Logit is based on a logistic distribution, different probability distribution. The Logit, the normal and the logistic distributions look very similar. They're both symmetric distributions. And regardless of which one we use, the approach is to do this. So again, the values in our data set, the y's are always ones or zeros. And so again, if we have data that are arranged this way, so we have a bunch of zeros down here for y, various values of x, a bunch of ones for y, various values of x. What we do in this case is to use a cumulative distribution of either the normal or the logistic as our regression line. And what that looks like is something like that. And again, we can say, for some value of x, we can use this regression line to predict the probability y equals 1 is going to be this. But what we like about using this cumulative distribution function is that its lower bound is 0 and its upper bound is 1. And so we never get probabilities outside the 1, 0 range, predicted probabilities. So using OLS is not uncommon with these kinds of models. And it's justifiable if most of the values are clustered together and toward the center of the distribution, because this part of the regression line looks an awful lot like that, right? And so if you don't have extreme values of x on either end, if things are clustered pretty much near each other, then the OLS model is not the worst thing in the world, but you're always better off using logit or probit in this case, okay? So when we use OLS, we know how to interpret the coefficients. Those are just linear coefficients. When we use logit or probit, the coefficients that we get are not easily interpreted. And so we have to work a little bit harder at interpreting those. It's also the case that the marginal effect of x differs depending on where it's measured. All right, we talked about this the other day, that the slope of this line is always the same. And so if we're asking what's the effect of a 1 unit change on x, it really doesn't matter where we're doing it. The effect is always the same. But here, the effect of a 1 unit change in x matters a lot. If we measure that 1 unit change here, the difference in the expected value of y is quite different than if we measure that 1 unit change, say up here or just about anywhere else. And so the magnitude of the effect of x is always changing as we move along this regression line, and that makes life more complicated. Okay? Anyone have questions? Okay. So what I want to do then is first let's look at some estimates. I'll bring my status screen up so you can see it. All right, so I've been playing around with various things here. Let me just scroll those off the page. And what I want to do is to use this data set, MROZ2. Rose is actually a guy's name. And we'll use that for a little bit of estimation, okay? And you can see that actually what this data set is about is whether or not people work or whether they're in the labor force. And so in the labor force is a dummy variable equal to 1 if a person is in the labor force and 0 otherwise. And you can see what these other variables are. Well, we're going to use some of them. I think we're not going to use that. All right. So, let's see, bring it back up here. All right. I've done, this is actually the first version of this I sent you didn't include this education category variable, but I added that. It seemed like it was easier for me to add it than to explain how to add it. These are all educational level variables. So this is less than high school, more than high school, and bachelor's degree, and then more than a bachelor's degree, some graduate work. I can enter those in my regression just as the dummy variables, and I'm going to leave high school out to make that the reference category. And I just want to do an ordinary least squares regression to start. So that's OLS. Okay, you with me? So here's an OLS regression. And there's nothing particularly unusual about it. You can see that the F statistic is big enough so that we can reject the null hypothesis that none of the variables belong. That makes sense. So these variables are number of kids less than 6 years old, age of the person. These are all married women. The wage that the woman reports earning at this time, husband's wage, family income, experience, and then the education variables. Actually, you know what? If I do that, you can see the means of each of those variables up here. I think we've talked about that before. When you do an OLS regression, if you just add this option means, it'll put the means of the variables in your regression. It will show those. All right, so this says that for every additional child in the household less than 6 years of age, that reduces the probability of being in the labor force by about 18%. Okay? Holding everything else constant. And in this ordinary least squares regression, it's 18% regardless of how old the woman is, regardless of what her family income is. It's a linear estimate, so it's the same regardless of what else is going on in the regression. Okay? We can take that same regression and estimate it using Probit, just substituting Probit for regress. And when we look at this output, we see a couple of things. One, we see that Stata goes through a number of different iterations as it estimates this regression. What Stata is trying to do is to find the maximum value of the likelihood function. And so it starts out here This is based, the first thing it does is an ordinary least squares regression for starting points. And then it has methods for looking around to see whether it can adjust the estimated values to make the likelihood function larger. And it goes all the way from -514 to -273. That's a big jump. And you can see that it keeps on improving the fit. It keeps on increasing the size of the likelihood function until it can no longer do so. And at that point, we say that the model has converged. And there's a whole literature on how to figure out when a model converges, and we're not going to deal with that. The output that we get tells us the number of observations. This thing, which I want to talk about, there's a pseudo R squared, a sort of a measure of goodness of fit, how well the data fit the regression that we've just estimated, and the value of the log likelihood function. Okay. If we come down to number of kids less than 6, we can see that it has a negative coefficient, which means that as the number of children less than 6 increases, the likelihood of being in the labor force goes down, but we can't interpret this thing directly. This 0.737 number doesn't have a clear interpretation. We would have to transform this in order for it to be meaningful. So when we look at the output from this probit regression, we can take the signs seriously. They tell us the direction of the effect, but the magnitudes we cannot read off of this output. Okay. And similarly, we could do a logit regression. So let's just remember that this coefficient is -0.737. So I'm going to do logit. You can see that logit does the same thing. It's trying to find the maximum value of the likelihood function. It finally converges here. Now this coefficient is -1.22. Again, we can't interpret that directly. The one thing we can do is to look at the sign. And again, this just tells us that there's negative effects when there's a negative sign and positive effects when there's positive signs. But that's about all we can say. Okay, questions? So, anybody? No. All right. So the first thing I want to do before we get to interpretation of these coefficients, which can be complicated. It can be straightforward and it can be complicated. The more clearly you understand it, the more complicated it gets. Before we do that, I want to talk about hypothesis testing with this kind of regression. And let me go back to the probit regression we did. All right. And so there are two kinds of test statistics that Stata is telling us about here. One is this chi-square value up here, and LR stands for likelihood ratio. And the other is these Z statistics here. And so let's talk about these in turn. Let's talk about likelihood ratio. And I'm going to switch cameras here. There we go. All right. So likelihood ratio test. So this thing is our likelihood function. We're not sure exactly what it looks like. When we do logit and probit, we're using normal or logistic distributions, and they look approximately like this. And what the likelihood ratio test does is this. It asks the question, by how much does the likelihood increase when we compare two versions of a model? And typically those two versions are going to be the constrained model and the unconstrained model. So we impose some sort of a constraint and we find the value of the likelihood function. We release that constraint and we again find the value of the likelihood function, and we're going to do a comparison of those two values. So what's it mean to constrain versus unconstrain the likelihood function? Nope. There you go. All right, in this model that I've estimated, I'm allowing Stata to estimate for me the effect of each of these independent variables, the effect of each of those on the probability of being in the labor force. This, what we have right here, is the unconstrained model, because we're allowing each of those effects to be estimated. A constraint would be, suppose I said, I'm going to estimate this regression under the assumption that all of these independent variables have no effect. So essentially what I'm going to do is estimate the model with no independent variables in it. What does that look like? It's going to look like this. All right. So here's a probit regression where being in the labor force is estimated as a function only of a constant, only an intercept. There are no explanatory variables. So essentially what I'm doing in this case is I'm forcing all of these coefficients to be zero. Right? I'm just leaving them out of the model. I'm not allowing them to be estimated. And what I find is that when all of those values, when all of those independent variables are left out of the model, so the coefficients are all zero, what I see is that the value of the log likelihood function is -514. And when I then allow Stata to estimate all of these coefficients, the value of the log likelihood function rises considerably up to -242. Okay, and the likelihood ratio test is based on a comparison of this constrained estimate of the likelihood function versus this unconstrained estimate of the likelihood function. Okay, so you with me? All right. So in what I just did, we had two versions of the model. In the constrained version, the value of the log of the likelihood function, according to the output, was -514.8732. And so that's maybe this height. And then when I removed the constraint, when I allowed those coefficients to be estimated, the log of the likelihood function rose up to 242, negative 242.82643. And that's maybe here. Okay. And so in the unconstrained version, I'm looking for the highest possible value of the likelihood function. In the constrained version, I'm forcing the value to be much lower. And what I want to do is essentially make a comparison of those two values. And the way I'm going to do it is I'm going to use a likelihood ratio. And so the deal is that the likelihood ratio, it's actually a ratio, one divided by the other. But when we take the log of the likelihood function, it becomes a difference rather than a ratio. And so this thing is computed as 2 times the log likelihood for the unconstrained version of the model minus log likelihood of the constrained version. So in our case, this means it's going to be 2 times the unconstrained version of the model minus 242.82643 minus, so that's going to be plus 514.8732. That then is 2 times 272.0467, which is 544.09. This is our likelihood ratio test statistic. And this is going to be distributed as a chi-square statistic with the number of constraints as the degrees of freedom. What's the hypothesis that we're testing? The hypothesis is that all of the betas are equal to 0 against the alternative that the betas are not equal to 0. So this is in ordinary least squares, this would be an F-test. Okay. So the constraint is what we get in the null hypothesis. The null hypothesis is that all of the betas are 0. That's our constrained version of the model. And our unconstrained version of the model is that at least some of the betas are not 0, and we're allowing them to be that. Questions? So let's see.
I have a question, please. So the two that we have here in the LR, so originally, was it squared? And then when you take the ln, it's like 2 times, or what? Where does it come from?
It comes from, it's initially minus 2 times the likelihood ratio. It's the likelihood of the unconstrained over the likelihood of the constrained.
Mhm.
That's the original version. That's the base version of the model. But when we take logs, it becomes this.
I see.
All right. So that's why it's kind of funny to call it a likelihood ratio when we actually compute a difference.
Hmm.
That's just because we're working with log likelihood.
I see. And it will always be positive, right? Since chi-square is always positive.
Yeah.
Okay. Thank you.
Right. It's got to be positive. It's chi-square. If you compute it and it's negative, it means you reversed these two things, and you should then change the sign.
Okay.
Right. I mean, the magnitude comes out the same regardless of how you do it, but it's got to come out positive.
Okay.
Okay.
Thank you.
Yeah. So when we run this full model with all the regression, with all the coefficients in it, Stata reports a likelihood ratio of 544.09, which is what we just computed. And so what Stata does is literally, it runs this regression with all the coefficients left out, with all the independent variables left out. And then it runs it again the way we've asked for it, and it computes that likelihood ratio this way, okay? Now, there are other things we could do with the likelihood ratio test. We could, just like with the F test, you can do a test on a subset of coefficients. You could do that here as well. Suppose what we do is to say, we want to know whether, taken together, all the education independent variables, whether they explain a part of the, or a significant amount of the variation in that decision of whether or not to work. So what we could do is go back, we can estimate the constrained model. That has a log likelihood of -250. We can compare that with the full model. Log likelihood of 242. And we can then test the hypothesis that as a group, these independent variables don't matter. Let's go ahead and compute that. So the likelihood ratio in this case is going to be 2 times the log likelihood for the unconstrained version. This is the unconstrained version. It has all the variables in it. That's -242.82643 minus the constrained log likelihood, 250.55136. I want Stata to tell me what this value is. And so what I'm going to do is to use this display function. I don't know if you've seen this before. I'm not sure if I've used that. We'll display 2 times, oops, 2 times this minus this, which I'll just put it as and so that's going to be, so here our likelihood ratio test statistic is 15.44986. And that's going to be distributed as chi-square with 1, 2, 3, 4 degrees of freedom. I can get a chi-square table here just by typing chi-table. And so I have 4 degrees of freedom. My critical value is 15.44, and that tells me that I can reject at the 1% level of significance. I can't quite reject at the 0.01 level of significance. Okay? And so I can conclude that taken as a group, these variables do belong in the model. Yep.
What was the unconstrained regression you compared it to? The 250 number.
Right. So the constrained, this is the constrained one, I took out, so the hypothesis that I'm trying to test is taken together, these things matter. So what I'm going to do is my null hypothesis will be that all these betas are 0. So I force them all to be 0 by taking them out of the model here.
Okay.
Okay. So
Yeah.
this is the constrained model, and this is the unconstrained model.
Oh, so you literally just typed in probate regression and got the unconstrained.
Yeah, that's right. So the likelihood ratio test is, it's a fine test, but what you see when you actually work through it like this is that one of the inconvenient things about the likelihood ratio test is that you have to estimate twice for it to work. You have to estimate the constrained and the unconstrained versions of the model. Okay, but that's doable. Have other questions? All right, so that's a likelihood ratio test. The other test that we're going to need to use is called the Wald test. And so anybody know who Wald was? He's a mathematician. And so Abraham Wald. And so the Wald test works a little differently than the likelihood ratio test. Again, this is our likelihood function. Under the Wald test, our null hypothesis is typically going to be that a coefficient is 0 against the alternative that that coefficient is maybe not 0. If this likelihood function is a standard normal, then its mean will be at 0. And so that's 0. And we go out and see what our actual estimated value of beta is, beta hat. And all we're doing is looking at the distance horizontally between the hypothesized value, the null hypothesis, and the observed value. And to compute the Wald test statistic, we're going to take beta hat minus the hypothesized value of beta divided by the standard error of beta hat. And that should look pretty familiar. Because when we do a t-test, the picture looks like this. The intuition is just like this. And the test statistic looks like this. a t-test is a test that can be done in finite samples, in small samples, or in large samples. The Wald test is a large sample test. Okay. And so, because it requires large sample, this difference in a large sample is no longer has a t distribution. It now has a z distribution. Right. So it's not t because n is assumed to be large. So the Wald test turns out to be pretty comfortable because it just looks like a t-test. And so if we want to do a Wald test on a particular coefficient, it looks just like to compute the z statistic, we take the coefficient minus the hypothesized value, which is 0. That divided by the standard error gives us a z statistic. And we've done this 1,000 times. Okay. We can also use the, and by the way, you can see that one advantage of the Wald test then is you don't need to do multiple estimates. You can do it based just on a single estimate, which makes it more convenient. We can also do a Wald test on multiple coefficients, and Stata makes it easy to do that. If I want to test these education variables, whether they're collectively equal to 0, I can say test, and I just name the variables. Oh, sorry, let me rerun that probit regression so we can get those closer together. I forgot the chi-square was there. All right. All right. And we end up with a chi-square when we do this for a single coefficient, it's a z statistic. When we combine coefficients, the Wald test is then a chi-square distribution with the number of degrees of freedom equal to the number of variables we include in there. And you can see that this comes out very similar to the likelihood ratio test. Okay. So those are the two basic kinds of hypothesis tests we'll do with maximum likelihood estimation. We'll do likelihood ratio tests and Wald tests. And they can be similar or different. We could, by the way, if we wanted to do a likelihood ratio test on a single coefficient, we could do that just by either dropping that variable or including it, and then comparing what happens to the likelihood value in the version where the variable is in the model unconstrained versus out of the model constrained. Okay, typically that's a little bit cumbersome and we just rely on the Wald test instead. The Wald test and likelihood ratio test are asymptotically identical, though in specific cases, the values are gonna vary a little bit. Questions? Yep. Andrew, go ahead.
Yeah. Then how would you know which one to use in the data set? Or you just do both?
How do you know which hypothesis test to use?
Yeah.
There are two ways to know. One is if I say to you, do a Wald test, then you know to do a Wald test. The other is if I say to you, do a test, You could do either or both. And typically, if what you want to do is to test whether all the variables taken together belong in the model, the easiest way to do that is going to be with a likelihood ratio, just because that's what's reported. And typically, if you want to do a test on an individual coefficient, it's going to be easiest with the Wald test, because that's what's reported. But you can use either test for any of these hypotheses.
Okay.
Anybody else? All right. So now we need to talk about interpretation. And I think what we'll do is to get started on interpretation, and we'll take our time going through this because it's confusing. Useful, but confusing. All right. So I have my probit regression here. And we talked about the fact that interpreting these coefficients is not straightforward. And what we need to do is to transform them somehow in order to be able to interpret them. And this becomes complicated because when we have these nonlinear models, which is where we're estimating a nonlinear regression, there are a variety of ways to think about how to interpret. So so one possibility is this, and what we're going to do is a command called the margins command, sorry. And the margins command does a whole bunch of different things. And we're going to try to limit the number of things we do with it just to things that are useful. So here's the first thing we can do. I'm going to say margins, comma, dy dx. I'm going to put an asterisk in parentheses. So what I'm asking Stata to do is to compute the derivative or the marginal effect of each of the independent variables. When I include the star, it tells it do all the variables in the model. Okay. And here's what I get. I get that on average, as the number of children less than 6 in the household increases by 1, we expect the probability of, in this case, the being in the labor force, we expect that probability to go down by about 13%. Okay, so this is more of a linear interpretation that we're used to. What we're getting here is what we would call an average marginal effect. And this is where it gets confusing. So let me come back and write a little bit. So when you type margins dy dx star, what you're going to get is an average marginal effect. So what does that mean? All right, we have a regression that looks like this. We have a regression line that's nonlinear. And what we can see when we look at this is that the effect of x on the probability y equals 1 is relatively small here. That the slope is low, and so the marginal effect is relatively small. And then that relative effect gets larger and larger and larger, and then it gets smaller and smaller and smaller. And so the magnitude of the marginal effect is changing as we move from one end of the regression line to the other. What the average marginal effect is it essentially computes the marginal effect all along this regression line, and then it just takes the mean of that. So it's the mean marginal effect. So that's a useful number, but you can see that it's not the only number you might be interested in. You might be interested in knowing when x equals 1 versus when x equals 3, what's the difference between those? The average marginal effect doesn't tell us that, but we can get to this. Okay, so what this shows us is, on average, how each of the independent variables affects the probability of being in the labor force in this case. So on average, a person with some graduate work is 18% more likely than a person with a high school education to be in. Remember that high school is the omitted category here. So experience has a small positive effect. Family income, for every $1,000 increase, you expect probability that you work to go up by about 0.3%. As a husband's wage goes up, women are less likely to work in this sample. As a woman's wage goes up, they're more likely to work. And we can now we can interpret these in a linear sense since they are marginal effects. Okay? Any questions about that? All right.
Professor, I have just a small question. Like, how did Stata know that the INLF was the dependent variable? Because when you typed margin comma dy dx star,
right.
Like, how did he know that like is it because it's the first on the list, or that it is the dependent variable, or how does he know?
So margins is a command that it's called a post-estimation command. It's a command that always comes after you've estimated something. And so what it does, Stata always holds the most recent thing you've estimated. It holds it in memory. And margins then uses whatever's in memory to compute this.
I see.
Okay.
Thanks.
All right, so this is the average treatment effect then, or the average marginal effect. And what we could do is to, instead of looking at a marginal effect, we could also ask Stata to estimate elasticities, which are useful. And what I want to do is just to show you a variety of options that you have for things that you can estimate. So to get elasticities, instead of dy dx, we type ey ex. And you can see that the probability of being in the labor force is elastic with respect to age. If age goes up by 1 year, the likelihood of being in the labor force goes down 1.41, which is a big decrease in probability, right? So it goes, I'm sorry, I said that wrong. This is an elasticity. If age goes up by 1%, probability of being in the labor force goes down by 1.4%. These are estimated in percentage terms. So age is elastic. The others are inelastic. If the number of kids goes up by 1%, probability of being in the labor force goes down by 0.23%.
Professor, sorry, you
Yeah.
said if age goes up by 1%, a probability goes down by 1.4%. Probability goes down.
Yeah. That's a dependent variable.
By 1.4%, right? Okay, so it's percent. Okay, yeah, that's what I was
It's an
doing.
elasticity. So it's the percentage change in dependent variable over percentage change in independent variable.
Yeah. So the dependent goes, okay, I heard like by 1.4, I didn't hear the percent, so it was like by 1.4%. Okay,
Yeah.
it's unit.
The
Yeah,
first time I said it, I screwed it up.
Okay. Yeah, that's what I was wondering. Okay, no, it's fine. Thank you.
And again, these are average elasticities. These measure what's going on over the entire range of the regression line, just as these derivatives or these marginal effects are over the entire range. So this is an average elasticity. Okay. We could, instead of estimating average elasticities, average derivatives, as we did here, we could ask, what are the values of the derivative, or what are the marginal effects if each value is at its mean? Because that's similar to what we do in OLS. And so in this case, I go back to my margins command, dy dx. So I'm asking for derivatives, and I'm going to say at means. When I do that, it tells Stata, unless I've indicated otherwise, to put all values at their means. And so it tells us what the means are for each value. And it then gives us the derivative at the mean of each value. So we're setting each value equal to its mean. And when all values are at their means, having another child decreases the probability of being in labor force by 0.19, from 19%. On average, that decreases 13%, taken over the entire range of values. But with everything at its mean, it's 19%. Okay,
And
so
so, sorry,
What?
so the difference in the interpretation will be just adding at the end of this, interpreting this coefficient when evaluated at its mean.
so it's with all the independent variables at their means.
Okay.
So so in the first case, what we're doing is we're taking the average of all the, essentially the average of all the slopes, you can think of it, all along the regression line, versus saying, we're going to make this X bar, and we're going to hold all the other independent variables also at their means, and we're going to figure out what the marginal effect is right at X bar, right at the mean. So you quickly start to see how this gets complicated. Yeah, Andrew?
Like, so what does the difference in 7% tells us? Or like 6% tells us?
Mm-hmm. So the difference is, for the average marginal effect, it's the average across the entire range of the regression line.
Mhm.
Right, we're taking the value here, plus here, plus here, plus here, plus here, plus here, plus here. We're taking all those values and we're computing the average. when I type margins dy dx star at means, what I'm telling Stata to do is to ignore values that are not at the mean. I'm only interested now in figuring out what happens when the independent variables are at their means. In this case, there's just one independent variable, x bar. And so I want to know what's the marginal effect right at this point. So the average marginal effect is over all possible outcomes. This specific marginal effect is only at the mean, only at one spot. And so let me just put these two next to each other. They're easier to see. All right. Just trying to change the font to make it, never mind. All right. So what this says is that the average effect of having one more child is to decrease the probability by 13.4%. Versus when all variables are held at their means, when we evaluate it at only one spot at the means, the effect of one more child is to reduce the probability of participating by 19%. I'm not seeing a flash of recognition. So,
but Professor,
yeah.
It makes sense that like when we evaluate at the mean, it will always be greater than whatever when we evaluate without evaluating at the mean, like the average, because at the mean it's where the slope is biggest. You know, knowing the shape of the probit. Isn't that true? You know, if you go like
yeah, you know, so your intuition is right when we have one independent variable, and that's the picture I'm showing you.
Yes.
But when we have multiple independent variables, I'm not so sure it's always going to work out that way.
I see.
Okay. But you're right that essentially what we're doing here is I'm taking the average slope over all values here versus the slope at the mean where it's at its steepest.
But adding them together can go like in the other direction. I see exactly what you mean. Thanks.
Yeah. Yeah, it's not a two-dimensional problem is the thing, right? It's so many dimensions that and that's why these things, these nonlinear models, these multivariate nonlinear models are really complicated to work with. And I think what I want to do, we've been at this for more than an hour. I'm going to stop here because I think we're at the point of no longer being particularly productive if I keep going, because there's a whole bunch more versions of this that we can consider. And I think what I will do is to stop here. There are a couple of things you can look at, one of which is actually the manual for Stata. If you look up the margins command, it goes through a variety of different things that command will do. Also, the Long and Fries book describes a lot of this. And so I think what I want to do is this. I gave you the data set, the one called binary. Let me just load that up. And we can talk about that. And I'll leave you with a little problem to play with. Okay, so this is a more manageable data set. This is college admissions. Whoops. 400 observations. You can see that about 31% of people are actually admitted. The independent variables are, these are graduate school admissions, so these are GRE scores going from 220 to 800. Grade point average from 2.2 to 4, and a rank. And so this is whether the person's class rank is in the top quartile, second quartile, third quartile, or fourth quartile. So let me just show you one thing to do with this, and then I'll leave you with a question to work on with this data set. The rank variable is like the educational categories variable in the other data set we were just looking at. The rank variable you can see it has 4 different values. And if we just include the variable in a regression, I'm not sure what it means to go from 1 to 2, right? I mean, they're categorical, but these values don't really mean anything. And so what we want to do is to essentially include these as a group of dummy variables. And we can do that this way. If we say regress probability of admitted versus GRE rank, and then I dot rank. If you include it that way, then the variable rank gets included just as a set of dummy variables. It omits one. Okay, so this is OLS. I'm not going to do the probe it or logit for you. You can do that. And the question I would ask you is, and see if you can figure out how to get at this, is how, this is clever of me, isn't it? I don't think stat is going to like this command, but it's all right. How does the probability of being admitted change? Actually, that's not quite what I want to say. Let me get this. How does the effect of GRE on the probability of being admitted change as GPA changes? That's the question I want you to try to think about. So GRE has an effect on being admitted. And the question is the effect the same if your GPA is 2 as it would be if your GPA was 3 or 3.5 or 4? So there's essentially sort of an interaction between GPA and GRE. And we can use the margins command to try to figure that out. And so I'm not certain you have the tools exactly right now to answer this question. But in the next class, we'll come back and work through that question. See if you can think about that between now and then. And we'll try to make some progress. Okay? All right.
Thank you, Professor.
Yeah. So there you go. And this is what you end up with.
Thank you.
Thanks, Professor.
You're welcome.
You
All right.
too.
Thank you, Professor.
Okay.
Take care of yourselves. I'll see you soon.
Bye.
Thanks.
Thank you.
Bye.
Thank you.